Hi, my name's Daniel. It's a pleasure to be here. I got to chat to a bunch of you. It's been a really great event so far, so thanks to the organizers. I'm the founder of a new startup called All Purpose Machines. We're building an API portal that sits directly in the IDE, designed to make integrations radically quicker. And previously, I was the technical co-founder of Hyperledger. Some of you might know is the first enterprise blockchain, which we ended up donating it to the brand to the Linux Foundation many years ago. So you might know it now, and it's quite a large Linux Foundation project. But I'm here today to talk about REST APIs. REST APIs, I've been building REST APIs for most of my career, something like 17 years. And a lot's changed in the space, I think we can all agree. I would say mostly the changes have happened outside of the API. We do a lot more in documentation. We do a lot more in writing specs. We do a lot more in SDKs. We didn't think about SDKs 17 years ago. We just shipped some raw endpoints. Thank you. But the actual kind of nuts and bolts, kind of the JSON over the HTTP, in my mind hasn't changed a huge amount in 17 years. And something about that seems somewhat crazy to me. We're trying to ship ever more sophisticated services to our customers. Data has gone up by a couple of orders of magnitude. We now live in the world of real-time streaming data. And I just wonder if something about some of the difficulties we have shipping very sophisticated services today could actually be tackled down fundamentally if we actually take a real look at what it means to build a REST API, and if we actually increase the capabilities, enhance the power of the lowest levels of our stack. And what happens if we could just snap our fingers and instantly upgrade the capabilities, the power of how we build REST APIs? I think we'd be able to build much better services that solve more customer problems more easily. They could be more easily integrated. I think there's some very interesting possibilities there. So this is the core of my talk. I think it's possible, and I think this is roughly the route that I see it happening. I think the future of REST APIs is client-side code execution, realizing that we can send more than just data from our servers to our clients. Our clients are computers, right? We can send code to execute on the client. And far from being some sort of weird research project that not many people have kind of any experience with, I'm going to show you that actually this is a really mature, well-understood technology, and that actually it's been a part of the REST definition since day one. We just haven't really been exploring it. And I'll introduce you to HyperMap, which is a new REST standard that I've been working on this year, which lets you start using some of these capabilities today. So that'll be kind of two halves of the talk. I think what I'm going to talk about here hopefully has a general appeal to anyone who's building APIs, REST APIs. I think they could be, there's kind of broad lessons here for how increasing the capabilities might change the design, might improve how you can build and ship these services. I think especially interesting, though, if your business is selling a particularly sophisticated service to customers. Because something that I see, having been on both ends of this particular process, is that if you need your customers to get integrated with your service before you start billing them, if you have a particularly complex integration process, you can lose customers. So I think it's of broad interest, this talk, but especially so if you're trying to ship really sophisticated stuff to customers, your business depends on it. So was anyone at Kevin's talk yesterday? Really good talk in the afternoon. This slide actually was very similar to one of his. We'll start kind of just going back right to the kind of definition. What is REST? REST, in its original kind of incarnation, has nothing to do with APIs. Right? REST is the architecture of the web. So not HTTP, not HTML, not servers, not browsers, the whole thing together, kind of how it all fits together. And there's lots of interesting stuff about REST. One of the most interesting things is that broadly, the architectural definition of REST comes about 10 years after the web started. So it's kind of a retroactive definition of architecture rather than something you think of, you design the architecture up front and then you build something to match it. And one of the interesting things about that is that Roy Fielding, the person who came up with the definition of REST, was trying to capture not necessarily just the technical underpinnings of why the web kind of mechanically worked, why it didn't break, but also why it was successful. Right? REST was getting defined about 10 years later, about kind of late 90s. The web had exploded in popularity. Something was clearly working. It was hugely successful. And so REST as an architecture was attempting to capture that as well, not just kind of the nuts and bolts of how it worked. One interesting thing is that REST is kind of the platonic ideal of the architecture behind the web. The web itself falls a little bit short. It's not perfectly RESTful. So one area that the web breaks down is from the kind of the pure REST model is cookies. Right? To this day, my bank still has a little warning, like do not press the back button when I'm doing certain things, and that's probably because some kind of terrible cookie state management piece. So REST is expressed as constraints, and there are 6 of them. You can go to Wikipedia, you can grab the list. This is the list. And so it's an interesting way. Roy Fielding was kind of drawing on some previous work kind of to express an architecture as a series of constraints. Broadly, I could sit down at a computer, I can start a blank project. I'm going to build something. I can build it however I want. I can design it however I want. But fundamentally, the web is this kind of global scale distributed information retrieval system. It's going to run over multiple computers. Some of them are going to have data, websites. Some of them are just going to be simple terminals. And so there is a client-server architecture. That's just an inherent constraint of REST. And so these first 4 constraints, client-server architecture, statelessness, cacheability, and layered systems, you broadly get from HTTP. Just putting some JSON, some XML over a HTTP, you're kind of going to get these properties fall out of your system. And that kind of arrived in the API world, kind of mid-2000s. I guess I chatted to a few people. We attribute it to Ruby on Rails supporting REST APIs about 2006. And those first 4 constraints kind of arrive pretty fully developed. The uniform interface is an interesting one. Anyone here, raise your hand, familiar with hypermedia? OK, so a fair few. Well, this is an API conference. So that's kind of the argument. That hypermedia kind of fits into that uniform interface constraint. We've had a bunch of, I think, even in this conference series, we've had a bunch of talks over the years about hypermedia. I'm not going to reopen that debate today. Go and check out those previous talks. They're really interesting, some really good stuff. I'm going to talk about the final one, which, to the best of my knowledge, no one's really spoken about in the context of REST APIs before. And it's the only optional constraint, which is kind of an interesting optional constraint, which is called code on demand. So, in the context of the web, what does code on demand mean? Broadly, JavaScript. Right? Web servers don't just ship HTML to the client, they ship JavaScript as well. Back in the days, it might have been a Java applet or a Flash applet, and nowadays you can also ship WebAssembly. Let's kind of boil it down to JavaScript. So this is a server sending some JavaScript to the browser to execute on the client machine. And why is that interesting? JavaScript lets us temporarily enhance the browser. So a web browser is great. I can fire it up, and I can point it to any website, and it's just going to load that website and going to let me interact with it. I don't have to keep downloading a bunch of different applications to access different services. The browser is this kind of universal agent. It's wonderful. It comes with a whole bunch of built-in features. It can render and style big blocks of text. It's got forms with kind of fields and buttons. All this stuff kind of comes built in. A whole bunch of like image media rendering. It's great. But if you're, say, Google, it's the mid-2000s, and you've got this cool idea for a new map product, and it's going to use a new type of control, a slippy map. You want the user to be able to click and drag around, and very smoothly it's going to load in tiles around where the user is kind of dragging to. That's not a built-in control for the browser. So you've got a few options. Number one, you could go to the browser standards, try and get this new control added, wait a couple of years for it to kind of go through the standards process, pop out an implementation. It's not great. You could build your own app. You could, you're going to have to support probably most of what a web browser does. Maybe you could fork one, add in your new control. But now you've just got a maintenance headache on your hand. You've got a whole new app just for this one new service. What they do instead, you're launching Google Maps. You just ship some JavaScript. And you can use features like Ajax, back in the day, we now just call it fetch, to load the tiles in the background. Hey presto, you've got this new control, this new capability in the browser that didn't exist before. It's great. And I think it's fair to say JavaScript on the web is quite popular. It's quite successful. Various measures have it at 98, 99%. I don't know quite how you measure this stuff. One way of seeing how popular it is, just try turning JavaScript off in your browser and browse around the web. See how much works. And we're all, I think, familiar with everything from jQuery back in the day to React now, these frameworks that live in the browser and really add a huge amount of value to the web. In fact, I'd go so far as to say that if the web lacked code on demand, not necessarily JavaScript, but if it lacked that feature, if you couldn't deploy code from the server to the client, that it would have been overtaken by a similar information retrieval system, which did support it. Like, I think this is kind of life and death for the web. It had to support code on demand in some sense, which kind of raises the question, we've got REST, we've got this definition, we know code on demand is an optional piece of that. We can see it's hugely successful on the web. Why aren't we exploring this in the API space? And so, earlier this year, I started work on HyperMap. It's a new standard. There's a couple of interesting things, but what we're talking about today is the fact that it supports code on demand. So that is broadly, you can push JavaScript or WebAssembly from the server to run on the client side. And there is something like a mini DOM. So the DOM is the interface that the browser exposes the web page to the scripts that it runs. There's a very small minimal version of that, which is also defined part of the HyperMap as the standard. And rather than having to figure out how you're going to load and execute code yourself or get your customers to do it, I've written Mech. It's an MIT-licensed open source universal client for any HyperMap service. So similar to the same way a web browser, you can point to any website. That is the goal with Mech. You don't write your own SDKs. The goal is you just grab Mech, point it to your service. Now, Mech's pretty bare bones at the moment. I've only been working on this for a few weeks, a few months. But the great thing is, if Mech doesn't do something that you want it to, just send some code, right? Temporarily enhance it. That's one of the great things about code on demand. So let's take a look at a few, like this might be quite abstract, I don't know, maybe people can kind of see where this might go, but here's a few things. I've been playing around with this for the past few weeks, past few months. Let's take a look at some of the things, some of the challenges that we have today that having this capability in our stack might solve. Number one, eliminating webhooks. I was doing some work recently with some APIs, webhooks. It's conceptually quite simple, right? Does everyone know? Hands up if you create or consume webhooks in some fashion. Okay, so at least half of you know what I'm talking about. So it is, if you have some long-running process, instead of your client polling repeatedly, let's be a bit more efficient. You give them a URL, and they'll post back when this task is done. Triggers a fetch of the new data, which is great if you have a URL to send over, but there's a whole bunch of situations where you don't. Maybe you're writing a native application, mobile application, desktop application. You don't really have a server with a URL to post to. There's ways to solve it. Similarly, even if you are writing like a SaaS backend or something, as we were, what if you're doing development on localhost, or you're doing tests in your CI server? And there's a whole bunch of blog posts and all sorts of stuff about how you can tunnel these things down to localhost. It kind of works, but it's all a bit awkward. So let's take a look at how you might solve that if you had the ability to run code on the client. So this is a HyperMap response. It looks like JSON. It's encoded in JSON. It's designed to be super easy to get going. So we'll start at the bottom. We can look. There's just a ticket ID and some status. It's pending. Maybe there's a ticket purchase process, and the ticket's going to check the availability or whatever. It might take a few seconds. Might take a couple of minutes. We want to let the user know when the purchase is successful. Instead of the webhook, you can see that we've got this @ symbol. It's an attribute that we can use to decorate our JSON responses with some metadata. In this case, for this talk, we're just looking at the script. We can add some behavior to this particular response. So if we look at the script, so this is something whoever is writing this service, would create and send at that URL, I can't remember what it's called, event handler, would send something like this. It's like a small snippet of JavaScript. And we can use the existing features, the existing APIs of the web. So one of those is SSEs, server-sent events, a very simple way to just broadcast unidirectional events down to the client. This is what a web page would do, right? It might open up an event source for the SSE URL, grab, which is what we do in line 1, and then we listen for the on message. We listen for an event to be fired down that particular URL, and hypermap.set is our way of updating the response that the client's looking at, and we'll set the status to the event data. There's no webhooks, no callbacks, like no routes that you have to worry about. Just in a few lines of code, we've encapsulated this notion that this JSON is dynamic. It can respond to events just with a little bit of scripting that we can do on behalf of our client. They don't have to worry about the mechanics setting up the webhook. So how would you use that as the consumer? How would you call that? Well, it would look like this. So this is mech. You'd open up that particular resource, mech.open, and you'd save that. Instead of working with responses, you work with these kind of browser contexts. I conveniently find that it's easy to call them tabs. That's kind of conceptually what they are. It's like you're opening tabs to keep a track of the different resources that you're working with. And so when we can actually write this kind of reactive style, we can watch the response that's there, and we can look for the change event, and we can log the fact that the status has changed. So this eliminates all that kind of complexity with callbacks, with webhooks, sorry. So use case 2, streaming data. Does anyone have a WebSocket API that they publish or consume in some sense, some live streaming data? So one thing, I come from the fintech world, this is, I think, something I'm seeing a lot. You have a JSON API, kind of REST API for your historical data, and you have a streaming endpoint for your live data. You've got 2 sets of documentation, 2 different ways of interacting with it. We can actually unify them into one. So here is an incredibly simple stock service. Don't build a stock API like this. But we have some tickers, some prices. And again, we're just attaching a script to this. What we want is these prices to be live, to update. And this looks very similar to our previous example, right? We're just going to open up a new WebSocket, and we're going to listen for events, we're going to parse them, and we're going to update the responses in line. And again, our clients, mech, can just bind to the change event, and you can say, when the Apple stock drops below whatever, do whatever you want. So you can kind of write these kind of reactive callback styles. Now, if anyone's familiar, these both examples looking at live data, if anyone's familiar with GraphQL, you'd say this looks a bit like maybe GraphQL subscriptions. What's good about this? This uses all your existing REST API stack. Maybe you've got these endpoints already. Let's look at something you couldn't do, though. On-device analytics. Let's say we want to analyze some data. It's got some sensitive information. It's got some privacy requirements, or it's financially sensitive, whatever it might be. If you're writing a GraphQL REST API, the traditional thing is you're going to send the data over to the server. It's going to do the analysis. Response is going to come back. What if we could push the analysis to the client? Data never leaves. So here we've got a very simple interface. Just got an input and output sentiment to do some sentiment analysis over some text, both set to null. Here is, you can see we can import an open source sentiment analysis. We can look for the input changing. We can set the output. So this is a sentiment analysis happening fully on the client. So to recap, I think code on demand is an essential part of REST. It was right there from the beginning. We should be exploring that capability in our APIs. And it is usable today with HyperMap. And here you can go on the website. It's all open source. It's all published. docs.allpurposemachines.com. Feel free to email me, Daniel at allpurposemachines.com, or just find me on Twitter. Find me on Discord as well. Thank you very much. Pleasure.